All right, welcome back. You know that feeling when you're cruising along with binomial expansion, everything makes sense, and then bam, you hit a problem where the power is negative, or that first term isn't a nice simple one. Well, if that sounds familiar, you are in exactly the right place. Today, we're going to tackle that exact scenario and turn what looks like a super tricky problem into a simple process you can use every single time. So you've probably nailed something like 1 plus x to the power of 4. No problem. But then your teacher throws this at you. It looks like a crazy fraction with a square root on the bottom, which is really just a sneaky way of saying 4 minus x to the power of negative 1/2. It looks like a total beast, right? But trust me, by the end of this, you'll see it's way less scary than it looks. So what's the real roadblock here? What's the big deal? Honestly, it just boils down to one little thing. All the formulas we've learned, all the muscle memory we've built up, it's all for the form 1 plus xn. So the question is, what in the world do we do when that first number isn't our old friend 1? And here it is. This is the secret sauce. This is the one move that unlocks the entire problem. The trick is to force it to look the way we want it to, and we do that by factoring out that a. But, and this is the part you can't forget, when you pull that a outside the bracket, it has to take the power n with it for the ride. And just like that, you've got a to the power of n times something that looks exactly like 1 plus something else to the power of n. Perfect. Of course, the same old rule applies. This whole thing only works if that something else, in this case x over a, has an absolute value less than 1. And hey, don't just take my word for it. This isn't some random trick I made up. If you crack open the textbook, you'll see this highlighted as the key point. This whole idea of factoring out the a is the official standard issue method for solving these things. It's the foundation we're going to build everything on. Okay. Enough with the theory, let's get our hands dirty and actually see this thing in action. We're going to walk through a classic example, nice and slow, step by step. Let's expand 2 plus x to the power of negative 3. Okay, here's our game plan, just 4 simple steps. Step 1, we use our key insight. We factor out that 2, making sure it drags the power of negative 3 with it. That leaves us with 1 plus x over 2 to the negative 3, which is perfect. That's the form we know how to handle. Step 2, we go to work on that inner bracket with our trusty binomial formula. Step 3, we expand it out and simplify the terms. And finally, step 4, don't forget about that 2 to the negative 3 we left waiting outside. We multiply it back into everything. And once you crunch all the numbers, this is what you get, our final expansion. It starts with 1/8, then minus 3/16 x, and so on. The big takeaway here is seeing how that 1/8 we pulled out at the very start has now been distributed into every single term of the answer. But hold on, we're not quite done. We absolutely have to state the condition of validity. The whole expansion we just did was based on that 1 plus x over 2 part, right? So the rule says that the absolute value of x over 2 has to be less than 1. You just multiply both sides by 2, and that tells us our beautiful answer is only valid when the absolute value of x is less than 2. All right, let's level up. We're moving into what I call the pro move. This is the kind of problem you see on exams that separates the people who just know the formula from the people who know the strategy. It looks messy, but here's the twist. We don't need the entire expansion. We are laser focused on finding just one thing, the coefficient of the x squared term. This is all about strategy, not just grinding through the math. So here's how we do this the smart way. First, let's rewrite it as a product. 1 minus 3x times 4 minus x to the power of negative 1/2. Now we start expanding that second bracket, but, and here's the key, we stop as soon as we get to the x squared term. Why? Because you gotta think ahead. To get an x squared at the end, there are only 2 ways it can happen. We can multiply the 1 from the first bracket by the x squared term from the second, or we can multiply the negative 3x by the x term. That's it. Everything else is just noise we can ignore. And if we look at the textbook solution, you can see this exact strategy in play. Here's the expansion of that second bracket. Now watch. They find the only 2 products that matter. First, the 1 hits the x squared term. Then, the negative 3x hits the x term. You just add those 2 little results together, and bingo. You've got your coefficient, negative 45 over 256. It's all about working smarter, not harder. All right, you've seen the method, you've seen the pro moves. Now let's really make this skill our own by applying it to a couple of fresh problems straight out of exercise 7D. This is where it really starts to stick. Let's start with question 1b, expanding 5 minus 2x to the power of negative 1. And you can see in the table, it's the same dance every time. First, rewrite it by pulling that 5 out, then expand the inner bracket, And finally, multiply that 1/5 back through all the terms you just made. The strategy is exactly the same. Now let's check out 2a. This one has a fun little twist. We're expanding 2 plus x squared to the negative 2. So now our variable term isn't just x, it's x squared. Does that break our method? Not a chance. As you can see, we just treat x squared over 2 as our new variable in the formula. We rewrite, we expand, we simplify, and look at the result. The powers go up in x squared and x to the 4th. Our method is tough, it can handle this stuff. Okay, you've done the practice reps. Time for the main event. Let's look at a problem taken straight from an actual exam paper. This is what it looks like when the training wheels are off, and it really counts. So the question is to expand 3 minus x to the power of negative 3 over 2. Okay, the numbers definitely look a bit uglier. We've got fractions, we've got square roots, but just take a breath and look at the game plan. Does it look familiar? It should. It's the exact same 4 steps. Rewrite, apply the formula, simplify, multiply by the constant. The process doesn't care if the numbers are messy. And here's our final answer. Yeah, I know, it's not exactly pretty, with all those square roots hanging out in the denominators, but that's just what happens when you have a fractional power. The most important thing to see here is that this messy but correct exam-level answer came from following that same simple, reliable 4-step process. So there you have it. We've taken apart the core concept, we've walked through textbook examples, we've even stared down a real exam question. You officially have the complete toolkit. So, guess what? It's your turn. Here's a perfect one from the exercises for you to try. Find the expansion for the cube root of 3x plus 8. Okay, first hint, rewrite it with a power. Now think, what's your goal? You need a 1 in that first spot, so you're going to factor out the 3 or the 8. Go on, hit pause and see what you can do. And if you want another challenge, try this one from an exam paper. Find the first 3 terms for x minus 1 to the power of negative 3. Now this one's a little bit of a curveball. Which term are you going to factor out to get it into the right form? The x or the minus 1? Think carefully about which move gets you to that 1 plus something form we need. Look, if there is only one thing you take away from all this, let it be this. I don't care how wild or complicated the problem looks. Your first job, your only job at the beginning, is to figure out how to transform it into that golden form. 1 plus something to the power of n. Once you get it there, the rest is just following the recipe. And I'll leave you with one final thought to chew on. We've been saying over and over that this only works if the absolute value of x over a is less than 1. But why? What actually breaks in the math if that number hits 1 or goes past it? What does it even mean for an infinite series to be invalid? That, my friends, is a doorway into a much deeper and cooler mathematical idea